Alright, in this video we're going to talk about ionic bonds, and these are bonds that generally form in the reaction between metals and nonmetals. Let's look, for example, at the reaction between solid sodium and chlorine gas to form solid sodium chloride. The enthalpy change for this particular reaction, the standard enthalpy change, is exothermic, and it's highly exothermic, minus 411 kilojoules for every mole of sodium chloride that's produced. Let's also look at this, say, for the reaction between solid iron and oxygen gas to form a type of iron oxide. The enthalpy change for this particular reaction is minus 1,118 kilojoules for every mole of iron oxide that's produced. These are highly exothermic reactions, so the reaction between metals and nonmetals to form ionic compounds releases an enormous amount of energy. And we usually think about energy and stability as inverse to one another, so as the energy of a system goes down, its stability goes up. And so the release of energy that occurs in this, we can sort of draw that here on a diagram. So we're going to write energy on this axis, and we'll just put the different reactants or products on this axis. So we can put, for example, solid sodium and chlorine gas. That's going to be relatively high in energy, and we know that because as we go from solid sodium and chlorine gas to solid sodium chloride, there's a release of energy, 411 kilojoules of enthalpy released. And so we have a decrease in energy, which indicates an increase in stability. Salt's a lot more stable than solid sodium and chlorine gas. So this stability is also reflected in what's known as the lattice energy. This can be thought of as the energy required to break apart the positive and negative ions that exist in the ionic lattice. The ionic lattice. You might remember that ionic substances do not exist as molecules, but rather as sort of these infinite arrays of alternating positive and negative charges that attract one another. And it takes energy to pull these apart. And you can sort of get a measure for what this strength of attraction is, that, the energy you need to pull all these ions apart, through what's known as the lattice energy. The lattice energy is measured as taking the gas phase cation and the gas phase anion and having them react to form the solid lattice. Kind of an interesting esoteric experiment, but nevertheless, when these lattice energies are measured, they come out to be quite exothermic. 786 kilojoules per mole for every mole of sodium chloride solid that's produced. All right, so we're going to look a little more deeply into the energy involved in the formation of a ionic bond. Remember, energy is released here. And we can relate this to Coulombs Law, where the energy, remember Coulombs Law is this law that describes the attraction between a negative charge and a positive charge. There's going to be some attraction there. And that energy can be measured as some constant K times the charge on the positive cation times the charge on the negative anion divided by the distance between the cation and the anion. It's just a law of electric charge. So let's say in this case we've got a plus 1 and a negative 1 separated by a distance of, we'll call this 1. And then in this case we'll take the same charge, a negative 1 and a positive 1, and we'll separate them by a distance that's 4 times larger. What's the difference in energy there? In this case, the energy would be the charges, 1 times 1 divided by 1. So let's see, this is going to be energy, would be whatever K is, times 1 divided by 1. That's just K. And in the second case, the energy, that's going to be K times 1 for the, positive and negative 1, In this case, we're going to divide by 4. And so we see that when we separate the two charges by a distance of 4, that's k over 4, or a quarter k, the energy associated with these two ions attracting, it's going to be 4 times easier to separate these than these two here. And so we would expect in an ionic bond, the closer you can get the positive cation and negative anion together, the closer you can get them together, the harder it's going to be to pull them apart. The further apart they are, the easier it's going to be to pull them apart. So that's one aspect of ionic bonding. The second aspect of ionic bonding deals with the charges. So if we go, energy is, remember, K times Q1, or Q positive times Q negative, over the distance between them. In this case, let's take a positive ion with a charge of +1 and a negative ion with a charge of -1, and we're going to set them at a distance of r is 1 apart. That's their distance. In this case, let's take a charge of +2 and a negative charge of -2 and also set them at a distance of 1 apart, r is 1. And calculate the differences in energy we'd expect here. Well, in this case, K is going to be, the energy is going to be K times 1 times 1, those are the charges here, divided by 1, the energy is just K. Here we've doubled both charges, so the energy is going to be equal to K times 2 times 2, those are the charges here, also divide by 1, that'll be 4K. So we see if we have two ions, positive and negative, separated at the same distance, if we increase the charges, then it's going to be tougher to pull these apart. And of course, it'll be easier to pull these apart. So there's two things. There's both charge and distance between ions that are important in determining the strength of an ionic bond. Now, based on this and what we already know, we're going to make some predictions. So let's see. We're going to look at lithium chloride. We're going to look at sodium chloride and potassium chloride, and we're going to estimate which of these has the strongest ionic bond. We'll also do the same for sodium fluoride, magnesium chloride, and magnesium oxide. And we're going to keep this in mind. E is K times Q1, Q positive times Q negative over the distance between them, R. For what we saw before, we're going to try to remember that larger charges, that means stronger ionic bonds, right? And the second thing is shorter distances between the ions, so shorter distances, that's the same thing, stronger ionic bonds, the closer they get together. So here, let's look at these particular ions first, because this tends to be the larger determinant of the strength of bonds. We go to charges first, and then distances second. So if I look at my periodic table, let's see, sodium fluoride. The sodium's going to have a +1 charge, right? It likes to lose 1 electron. And the fluorine's going to have, the fluoride I should say, is going to have a -1 charge. Here, with magnesium, we're going to have a +2 charge, and the chlorides are going to have a -1 charge. And then with magnesium oxide, the magnesium has a +2 charge, and the oxide will have a -2 charge. So if I was going to compare these in terms of the strength of their ionic bonds, we would say magnesium oxide is going to have a stronger ionic bond because of larger charges, a plus and -2. That's going to have stronger ionic bonds than magnesium chloride, which is going to be a +2 and a -1, which we'd expect to have a stronger ionic bond than sodium fluoride. Now let's look at this over here. This is a little different because in this case we've got all chloride ions, so these are all going to be -1s. And they're all paired with alkali metals. So these are all +1. So in this case, the charges are equal. So we can't differentiate between these on the basis of charge. We have to look to distances. Well, how in the world are we going to tell the differences in distances between the cation and the anion in these? Well, we're going to remember this idea that as you go down a family, what happens to the size of ions and why? Remember, as you go down a family, you're adding shells. And so as you go down a family, because you're adding shells, the cation is going to be getting bigger and bigger. So what I'm doing here is I'm drawing the relative sizes between a lithium cation, a sodium cation, and a potassium cation. And in all these cases, your chloride ions, that's going to be about the same size. So I'm going to try to draw an anion here that's roughly the same size in each case. And we can see the distances between these centers, it's going to increase because of the increasing size of the cation. So let's see if shorter distances between the positive and the negative means stronger ionic bonds, then we're going to expect that the strength of these ionic bonds is going to increase in this direction. So we would expect that lithium chloride is going to have a stronger ionic bond than sodium chloride, which is going to have a stronger ionic bond than potassium chloride. And if we look these values up, indeed, this is the case. Lithium chloride has a lattice energy of about 840 kilojoules that's released when the ions snap together. Sodium chloride has a lattice energy of about 770 kilojoules that's released upon the formation of this bond. And potassium chloride has a lattice energy of about 700 kilojoules per mole for the snapping together of these particular ions.